The universe operates on rules that defy common sense. By the end of this video, you will have explored 25 bizarre space theories that challenge everything you think you know about reality. Could the laws of physics be a cosmic illusion? Might your own consciousness shape the world around you? What if our existence is nothing more than a fragment of something far stranger, something that pushes the boundaries of science and imagination? These ideas will test your assumptions one by one, each more unsettling than the last. So how far are you willing to question the nature of everything? The line dividing a plausible hypothesis from a bizarre theory is surprisingly thin. In cosmology and theoretical physics, an idea earns the label bizarre when it stretches the available evidence to its breaking point, often emerging from the elegant mathematics of equations or from stubborn anomalies that refuse to fit into any comfortable explanation. These theories are not wild guesses or science fiction. They are grounded in real data and rigorous logic, but they push so far beyond everyday experience that they feel more like sorcery than science. A theory becomes bizarre when it forces us to reconsider the basic furniture of reality, when it suggests that space, time, matter, or consciousness might be radically different from what our senses tell us. And here is the crucial point. Bizarre does not mean unscientific. It simply means that the idea currently sits at the far edge of what evidence can confirm or refute. These are the hypotheses that keep physicists awake at night, not because they are wrong, but because they might be right. Take the concept of fine-tuning, for example. The universe we observe appears to have a set of fundamental constants, numbers like the strength of gravity or the mass of a proton, that are precisely calibrated for life to exist. If any of these numbers were off by even a tiny fraction, the universe would be a cold, dead void or a searing plasma, with no stars, no planets, and no observers. The odds of such a perfect balance happening by chance are astronomically small. So what do we do with this fact? One response is the anthropic principle, which says that we can only observe a universe that allows observers to exist, so the fine-tuning is a kind of selection bias. But that explanation feels thin to many scientists. A far more unsettling possibility is that our universe is just one among an unimaginably vast multiverse, each with different constants, and we happen to live in the lucky bubble that supports life. That idea pulls the rug out from under our sense of cosmic significance. It suggests that the laws of physics are not universal laws at all, but just local quirks of our particular patch of reality. And that is exactly the kind of thought that earns a theory the label bizarre, not because it is scientifically invalid, but because it challenges the very foundation of what we mean by universe. That line of thinking that our universe might be just one bubble in an endless foam of realities opens the door to an even stranger possibility. What if none of those bubbles are real in the way we understand the word? What if our entire universe, every star, every memory, every thought you are having right now, is nothing more than a computer simulation running on a server somewhere in a higher dimensional reality? This is the simulation hypothesis, and it is one of the most unsettling ideas in modern philosophy and physics. The argument for it comes largely from Nick Bostrom, a philosopher at Oxford. He laid out a simple but powerful logic in the early 2000s. If a civilization ever reaches a point where it can create simulations of conscious beings, and if that civilization has any interest at all in running such simulations, then the number of simulated minds would almost certainly dwarf the number of biological ones. From a purely statistical standpoint, it becomes far more likely that you are living inside a simulation than outside one. After all, if there are billions of simulated universes, each containing trillions of simulated people, and only one real universe with a few billion actual humans, the odds of being among the simulated are overwhelmingly high. Bostrom called this the simulation argument, and it does not rely on any exotic physics. It simply follows from the assumption that computing power will one day become advanced enough to simulate consciousness. That raises a dizzying possibility: nested simulations. A civilization running a simulation might itself be simulated by a higher civilization, and that one by another, stretching upward into a potentially infinite stack of realities. Each layer would think it is the base reality, but none would have any way to prove it. This idea challenges the very foundation of what we consider real because it strips away any absolute reference point. If you cannot tell whether you are in a simulation or not, then the concept of objective reality becomes slippery. Our brains evolved to interact with a world of solid objects and consistent laws, but those laws might simply be the rules programmed into the simulation. And if the programmer decides to change those rules, reality itself would shift without warning. What does this mean for free will? If the simulation is deterministic, if every particle follows a pre-written code, then your choices might be no more free than the path of a character in a video game. Or perhaps the simulation allows for randomness, which could mimic free will but still be under the hood of the code. Either way, the idea that your decisions are entirely your own becomes harder to defend. Some thinkers have even suggested that the simulation might be running at a limited resolution, only simulating full detail when someone actually observes something. That would explain certain quantum mechanics puzzles, but it also implies that much of the universe does not exist until you look at it. Is there any way to test whether we live in a simulation? A few scientists have proposed looking for potential glitches in the fabric of reality. For example, cosmic rays, high-energy particles from space, should follow a very specific spectrum. But if our universe is a simulation with a finite resolution, like a digital grid, then at extremely high energies, those particles might show signs of that grid. Researchers have searched for these signatures in data from observatories, and so far they have found nothing conclusive. The absence of evidence does not mean the hypothesis is wrong. It could simply mean that the simulation is very well constructed, or that the glitches occur at energy levels we cannot yet probe. The simulation hypothesis does not just challenge our physics. It challenges our sense of identity. If you are a simulated being, then everything you value, your relationships, your achievements, your suffering, all of it is just information processing inside a cosmic computer. That can feel deeply unsettling, even nihilistic. But some philosophers point out that even if we are simulated, our experiences are still real to us. The pain you feel, the joy you feel, they are generated by the same neural processes, whether those neurons are biological or simulated. The experience itself is the only thing that matters. So the simulation hypothesis does not necessarily rob life of meaning. It just asks us to question the nature of the stage on which that meaning plays out. And that question, whether the stage itself is truly solid or just a brilliantly rendered illusion, may never have a definitive answer. One of the most unsettling ideas in cosmology questions whether your own mind is a bizarre accident. It is called the Boltzmann brane paradox, and it emerges from a simple but deeply troubling thought experiment. Imagine a universe that is infinitely old and filled with particles moving randomly. The second law of thermodynamics tells us that disorder, or entropy, always increases. But in such a chaotic system, tiny random fluctuations can occasionally create ordered structures. For example, a few molecules might briefly arrange themselves into a perfect crystal before dissolving back into chaos. The probability of such an event is staggeringly small, but if the universe is infinite in time, then even the most unlikely events will eventually happen. Now scale that idea up. What is the most unlikely structure that could form? A fully functioning human brain, complete with memories and consciousness, could theoretically assemble itself from random particles. It would be a fleeting moment of order, a ghost in the chaos, lasting only a fraction of a second before dissolving. But in that instant, that brain would believe it had a past. It would remember a childhood, a life, a universe full of stars and galaxies. All of those memories would be false illusions generated by the random arrangement of its neurons. Here is where the paradox bites. In an infinitely old universe, random fluctuations should produce far more of these isolated brains than they produce entire universes like ours. After all, a single brain is a much simpler configuration than a cosmos with billions of galaxies. The number of ways particles can arrange into a brain is enormously larger than the number of ways they can arrange into a stable expanding universe. So statistically speaking, any conscious observer should expect to be a Boltzmann brain, a momentary flicker of false awareness, rather than a biological human embedded in a long cosmic history. If that is true, then your memories of the past, your sense of identity, your confidence that the sun will rise tomorrow are all likely illusions. The very fact that you are listening to this video, that you experience a coherent stream of time and a universe that seems stable, contradicts the statistical prediction of an eternal chaotic universe. This is why many cosmologists find the idea disturbing. It pushes us to ask whether our universe could really be infinitely old, or whether some other principle prevents these fleeting brains from overwhelming reality. The paradox also ties directly into the fine-tuning problem. If the universe had different physical constants, it might not be able to produce complex observers like us, but it could still produce Boltzmann brains. So why do we see an orderly universe instead of a random flash of consciousness? The question has no easy answer, and it forces us to reconsider the foundations of time, entropy, and even the meaning of observation itself. The holographic principle turns the solid universe into a cosmic illusion rooted in information. It emerged from a strange clue found in black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that black holes have a temperature and an entropy, a measure of disorder that is proportional to the surface area of their event horizons, not to their volume. This was deeply puzzling. Entropy usually scales with volume, so why would a black hole behave so differently? The answer, proposed by the Dutch physicist Gerard T. Hooft and later developed by Leonard Susskind, was that the interior of a black hole might be a kind of hologram. All the information about the three-dimensional region inside could be encoded on the two-dimensional surface of the event horizon, like a cosmic hard drive. This led to a radical generalization. If black holes can store the entirety of their interior on a surface, then perhaps the whole universe works the same way. The holographic principle suggests that our three-dimensional space and the flow of time are not fundamental features of reality. Instead, they emerge from a deeper layer of quantum information written on a distant two-dimensional boundary, a surface that exists at the edge of the observable cosmos. We perceive depth and volume because our brains evolved to interpret that information in a certain way, but the true substrate of reality might be flat like a cosmic film. This idea has profound implications for gravity. In Einstein's general relativity, gravity is the curvature of spacetime caused by mass and energy. But under the holographic principle, that curvature might be an illusion, a side effect of how information is organized on the boundary. Gravity becomes an emergent force, not a fundamental one. This could resolve the long-standing conflict between general relativity and quantum mechanics, because the seemingly incompatible theories might be two different descriptions of the same underlying holographic data. Experiments are still far from testing this directly, but mathematical models of toy universes, such as those in string theory, have shown that a lower dimensional boundary can indeed encode all the physics of a higher dimensional interior. The holographic principle reshapes our understanding of reality by demoting space and time from the stage of existence to mere players on that stage. It forces us to ask what is truly real, the solid world we touch or the information that gives rise to it. And that question points directly toward an even stranger possibility, one that takes the idea of information and runs with it all the way to a digital universe. Black holes pose the deepest challenge to our understanding of information itself. In the 1970s, Stephen Hawking made a startling discovery. When he applied quantum mechanics to the event horizon of a black hole, he found that black holes are not completely black. They slowly emit a faint glow now called Hawking radiation. This radiation carries away energy, causing the black hole to shrink and eventually evaporate completely. That sounds straightforward, but it hides a devastating problem. According to quantum mechanics, information about any object that falls into a black hole should be preserved. If you throw a book into a black hole, the quantum state of every atom in that book should be encoded in some way, even after the black hole evaporates. But Hawking's calculation suggested that the radiation coming out is random and carries no information about what fell in. When the black hole is gone, the information seems to be lost forever. That violates a cornerstone of quantum theory called unitarity, which says that quantum information can never be destroyed. It can be scrambled or transformed, but it cannot simply vanish. This became known as the black hole information paradox, and it has tormented physicists for over 40 years. If Hawking was right, then either quantum mechanics or general relativity must be fundamentally wrong. Both theories are exquisitely tested, so neither can be easily discarded. The search for a resolution has produced several creative possibilities. One idea is that information does escape, but in a hidden form. Hawking radiation might contain subtle correlations between particles that encode the missing information, even though it appears random. This would require the black hole to act like a kind of quantum encoder, preserving information in a non-local way. Another proposal is that the black hole does not evaporate completely. Instead, it leaves behind a tiny stable remnant, a Planck-sized object that contains all the information. But such remnants would have to be produced in vast numbers, and they would behave in ways that seem to conflict with other aspects of physics. A third and more radical solution is the holographic principle we touched on earlier. If all the information about the black hole's interior is actually stored on its event horizon surface, then as the black hole evaporates, that information could be transferred back into the universe through the radiation. The holographic idea suggests that the three-dimensional world inside is a projection of two-dimensional data, and in that framework, information is never lost, it just changes form. So far, no single resolution has been universally accepted. Each attempt requires us to modify our understanding of space, time, or quantum mechanics in profound ways. The information paradox highlights how the borders of physics often become battlegrounds where our most cherished principles collide. And it turns out that similar contradictions lurk in other corners of cosmology, waiting to be confronted. Eternal inflation takes the Big Bang and turns it into an endless storm of creation. The idea grew out of the standard inflation theory proposed by Alan Guth in the late 1970s to explain why our universe appears so smooth and flat on large scales. Inflation posits that a split second after the Big Bang, a form of repulsive gravity caused space to expand at an exponential rate, stretching out any irregularities and leaving behind a uniform cosmos. But later physicists, including Andre Linde and Paul Steinhardt, realized that inflation might not stop everywhere. In most regions, quantum fluctuations can keep the inflationary field fluctuating, so that even while some patches stop inflating and become ordinary universes, other patches continue inflating forever. The result is a perpetually expanding foam of space, where new bubbles of vacuum constantly nucleate and then expand. Each of these bubbles becomes its own universe, completely disconnected from the others by vast stretches of inflating space. And crucially, the quantum fluctuations that trigger each bubble can cause the fundamental constants of physics to vary from bubble to bubble. In one universe, the strength of gravity might be slightly different. In another, the mass of an electron might be larger or smaller. The number of dimensions itself might change. This is the eternal inflation multiverse, and it yields an infinite number of distinct universes, each with its own unique laws. That idea offers a powerful way to explain the fine-tuning we observe in our own universe. Rather than assuming some cosmic designer set the constants perfectly for life, the multiverse suggests that we simply happen to live in one of the rare bubbles where the constants allow stars, planets, and conscious observers to exist. In the vast majority of bubbles, the constants produce dead, chaotic, or impossibly short-lived universes, but we do not live in those because there is no one there to observe them. This is a selection effect, not evidence of design. The multiverse turns the fine-tuning puzzle on its head, transforming an apparent miracle into a statistical necessity. Yet for all its explanatory power, the multiverse faces a profound difficulty. Because each bubble universe is causally disconnected from every other, there is no way to send signals between them. We cannot detect the existence of another bubble directly. We cannot measure its constants or observe its stars. The multiverse hypothesis is, by its very nature, almost impossible to test. Some scientists argue that if a theory makes no testable predictions, it ceases to be science. Others counter that the multiverse does make indirect predictions, such as certain properties of the cosmic microwave background radiation that might bear the signature of bubble collisions. These searches have so far turned up empty. The multiverse remains a tantalizing but unconfirmed vision, one that stretches the very definition of what it means to have a scientific theory. And this tension between explanatory power and untestability is a theme that will appear again as we confront the next bizarre theory. Quantum mechanics offers its own version of a branching reality. It comes from a radical interpretation proposed by a young American physicist named Hugh Everett in the 1950s. At the time, the dominant way to understand quantum theory was the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. That view said that before a measurement, a quantum particle exists in a superposition, a ghostly combination of all possible states, but when you measure it, the superposition collapses instantly into a single definite outcome. The collapse is not explained by the mathematics. It is simply imposed as a rule, a kind of cosmic coin flip that decides which reality we experience. Everett found this deeply unsatisfying. He asked a simple but devastating question. What if there is no collapse? What if the mathematics of quantum mechanics, the wave equation that describes superpositions, is literally true at all times? In his formulation, every time a measurement happens, the universe does not choose one outcome. Instead, it splits into multiple branches, each containing a different result. The observer also splits, so in one branch you see the particle spin up, and in another branch you see it spin down. Both versions of you are equally real. Both continue to exist, completely unaware of the other branch. This is the many worlds interpretation. It resolves the measurement problem by eliminating the mysterious collapse entirely. The wave function never collapses. It simply evolves and branches, creating an ever-growing tree of parallel universes. Every quantum event, the decay of a radioactive atom, the path of a photon through a double slit, the interaction of a particle with a detector, triggers a new set of branches. The result is an unimaginably vast and constantly splitting multiverse. Each branch is a fully realized reality with its own history, its own version of you, and its own future. And since quantum events happen everywhere all the time, the number of branches doubles with each passing moment, producing an infinite proliferation of worlds. This idea forces us to confront a staggering question. What does probability even mean in such a cosmos? In our everyday life, we assign probabilities to uncertain events. A coin flip has a 50% chance of landing heads, but in many worlds the coin does land heads in half of the branches and tails in the other half. Every possible outcome occurs with certainty, so when you say the chance is 50%, you are actually describing your ignorance of which branch you will find yourself in after the split. But because you split as well, every version of you experiences one outcome with total certainty. The concept of probability becomes a kind of self-location problem. How do you know which branch you are in before the measurement? You do not, and that is exactly what the probability numbers encode. This interpretation has profound implications for free will, identity, and the nature of reality itself. If every choice you make spawns a new universe in which you made a different choice, then in some sense all possible versions of your life are real. The you that stayed in bed, the you that took a different job, the you that moved to another country, they all exist somewhere in the branching tree. This can be both liberating and disorienting. Liberating because it suggests every possibility has been realized, and disorienting because it challenges the uniqueness of your own path. Physicists remain deeply divided over many worlds. Some embrace it as the most straightforward reading of quantum mechanics, free of extra assumptions like collapse. Others reject it as ontologically extravagant, multiplying unseen worlds without necessity. But it remains one of the most elegant and bizarre solutions to a problem that has haunted physics for nearly a century. And as we will see, other interpretations choose to solve the same mystery in entirely different ways, each with its own strange consequences. The many worlds interpretation sidesteps fine-tuning, but another idea puts the observer front and center. This is the anthropic principle, and it comes in two very different flavors. The weak version is almost a statement of the obvious. We exist as observers, so the universe we observe must be capable of supporting observers. That is a simple logical fact. If the universe were not suitable for life, we would not be here to notice it. The weak anthropic principle does not claim that the universe was designed for us. It simply says that our observations are biased by the condition that we are alive to make them. For example, if you look out at the night sky and see that the Earth is positioned at just the right distance from the Sun to support liquid water, that is not evidence of cosmic purpose. It is a selection effect. If the Earth were not in that zone, there would be no astronomers to marvel at it. This principle helps explain why the fundamental constants appear so finely tuned. Out of all possible universes, we can only exist in the tiny fraction where those constants allow stars and planets and chemistry to work. So the fact that our universe looks fine-tuned is exactly what we would expect, even if the constants were randomly chosen across a vast multiverse. That is the weak version, and most physicists accept it as a useful reminder of observational bias. But the strong anthropic principle goes much further. It suggests that the universe must have properties that allow life to arise at some point in its history. This could mean that the laws of physics are somehow compelled to produce observers, either by a hidden necessity or by a kind of cosmic purpose. Some formulations even imply that the universe was designed with life as its goal. This version is deeply controversial because it edges into metaphysics rather than empirical science. It does not make predictions that can be tested. Instead, it offers a philosophical answer to a scientific question. Critics argue that the strong anthropic principle is a tautology dressed up as a principle. It says the universe is the way it is because it must be that way, which explains nothing. Others defend it as a legitimate interpretation of the fine-tuning data, pointing out that a universe that could not produce life would have no observers to note its existence. But that logic actually belongs to the weak version. The strong version adds an extra claim that the universe is in some sense required to produce life, and that is a leap that many scientists are unwilling to take. The controversy boils down to whether the anthropic principle is a genuine scientific tool or merely a philosophical truism. Science works by making falsifiable predictions, and neither version of the anthropic principle predicts anything new. They only explain why we observe what we do after the fact. This has led some to call it a circular argument, a way of saying that things are the way they are because they are. But even its critics admit that the weak anthropic principle is useful for cutting through the illusion of cosmic conspiracy. It reminds us that our perspective as observers is not neutral. We are embedded in a universe that we can only perceive from the inside, and that internal viewpoint shapes everything we see. The strong version, however, pushes beyond science into questions of purpose. Does the universe have a goal? Are the laws of physics directed toward the creation of conscious minds? These are ancient questions, now dressed in modern scientific language, but they remain just as unanswerable as ever. The anthropic principle does not resolve the fine-tuning puzzle. It reframes it, and in doing so, it forces us to confront a deeper question, one that lies at the heart of all these bizarre theories. Is there a reason behind the cosmic order, or is the order itself just a product of our own existence? Black holes have always guarded their secrets behind a veil of darkness, but one of the most brilliant physicists of our time proposed that this veil is not accidental. Roger Penrose, the same mind who won a Nobel Prize for his work on black holes, introduced a hypothesis in the late 1960s called cosmic censorship. The idea is simple yet profound. Every singularity, every point where gravity becomes infinite and the laws of physics break down, must be hidden behind an event horizon. You can never see a naked singularity. There is always a black hole's boundary standing between you and the raw chaos at its core. Penrose argued that nature abhors a naked singularity because it would violate one of the most cherished principles in physics, determinism. Determinism is the idea that given a complete description of the universe at one moment, you can, in principle, predict every future moment. A naked singularity would shatter that. If you could observe an infinite point directly, you would see physics breaking down, and you could send signals out from that region, signals that carry information about the breakdown. That would mean the future is not determined by the past alone. It would depend on something fundamentally unpredictable, like the exact nature of the singularity itself. In other words, the universe would become chaotic in a way that no equation could tame. For decades, most physicists accepted cosmic censorship as a reliable rule. It felt natural because it kept the universe tidy and predictable. But recent computer simulations have started to challenge that comfort. When researchers run models of certain types of gravitational collapse, particularly in higher dimensions or with exotic forms of matter, they find that naked singularities can indeed form. The event horizon fails to form fast enough, leaving the singularity exposed for an observer far away to witness. These simulations are not just mathematical curiosities. They raise the real possibility that somewhere in the universe, perhaps in the violent death of a star or in the collision of two massive objects, a naked singularity could be born. If that ever happens, it would be a cosmic laboratory where we could directly probe the limits of general relativity and glimpse the quantum nature of gravity. Astronomers have not yet found any evidence of a naked singularity, but the search continues. Some have suggested that certain objects catalogued as quasars might actually be naked singularities, though the evidence remains inconclusive. This tension between theory and simulation leaves us with a fascinating uncertainty. Is cosmic censorship a true law of nature, or is it just a convenient assumption that will eventually be broken? The answer could reshape our understanding of causality itself. But even as we ponder the hiding of singularities, another mystery about the nature of time itself begins to emerge. Time feels like a river flowing in one direction, but some physicists suspect it is an illusion. The Wheeler-DeWitt equation, a central piece of canonical quantum gravity, describes the entire universe as a single static wave function. In this equation, time simply does not appear. There is no variable for past, present, or future. The math treats the cosmos as a frozen snapshot, a timeless quantum state that contains all possible configurations at once. This is called the problem of time, and it has haunted quantum gravity researchers for decades. If the fundamental law of the universe has no time coordinate, then our everyday experience of moments passing, of clocks ticking, of memories piling up must be an emergent property. It arises from some deeper, static reality. How could that be? One analogy is a film strip. Each individual frame is still a single image, but when you run the film through a projector, your brain stitches those frames together into a moving story. In the same way, the universe might be a collection of timeless snapshots, and our consciousness moving through them creates the sensation of flow. The arrow of time, the fact that we remember the past but not the future, might be a byproduct of the way information is processed inside that static block. Some physicists, like Carlo Rovelli, argue that time is not fundamental but emerges from the relationships between events. Under this view, the universe does not evolve in time. Instead, time evolves inside the universe as a kind of local approximation. This has profound implications. It means that the Big Bang might not be a beginning in time but just a boundary in the timeless wave function. The future might already exist, every possible outcome already encoded in the static equation, and our sense of moving forward would be like a needle tracing a path across a phonograph record, a journey through a landscape that already contains all the grooves. This idea challenges everything we think we know about cause and effect. If the universe is frozen, then your birth, your choices, your death all exist simultaneously. The distinction between past and future becomes a matter of perspective, not of reality. And that perspective might be tied to the way entropy increases, a concept that itself may be a statistical illusion. The Wheeler-DeWitt equation remains unresolved, and the problem of time is still an open wound in theoretical physics. But it points toward a universe far stranger than our common sense allows, one where the ticking clock is just a story we tell ourselves, not a fundamental law. This search for what lies beneath the flow of time leads directly to one of the most mysterious forces in modern cosmology, a force that seems to be pushing the universe apart at an accelerating rate. An invisible threat lurks in the very fabric of empty space itself. According to particle physics and cosmology, the vacuum that surrounds us might not be the truest, most stable state of reality. It could be what physicists call a false vacuum, a temporary arrangement of energy that appears stable but is actually perched on the edge of a much deeper valley. If that is the case, then at any moment, a random quantum fluctuation could trigger a transition, a decay, into the true vacuum, the lowest possible energy state. The result would be catastrophic and absolute. This process is known as vacuum decay. It would begin with a tiny bubble of true vacuum forming somewhere in the universe, a microscopic seed no larger than a subatomic particle. Inside that bubble, the laws of physics would be different. The masses of particles, the strengths of forces, even the number of dimensions might change. And that bubble would expand outward at nearly the speed of light, because the true vacuum inside is energetically favored. So the bubble wall accelerates as it consumes everything in its path. There would be no warning. No signal could travel faster than the bubble itself. So the moment it reaches Earth, every atom, every star, every galaxy would be instantly converted into the new vacuum state. All structures, all memories, all of history would vanish in an instant, replaced by a completely alien physics. This is not science fiction. It is grounded in actual measurements of the Higgs boson, the particle discovered at CERN in 2012. The mass of the Higgs is about 125 giga-electronvolts, and that value, combined with the mass of the top quark, suggests that our vacuum is metastable. The calculations are not certain. There are uncertainties in the measurements and in the theory, but the best current data indicate that the universe is sitting in a local minimum, not the global one. The chance of decay occurring in any given region within the next billion years is astronomically small, on the order of 1/10 to the power of several hundred. But small is not zero, and if the universe is infinite, then somewhere, sometime, a bubble will nucleate, From our perspective, the decay could happen at any moment without any cause or detectable precursor. The universe you know could simply be replaced in an instant, leaving no trace that anything ever existed. This sobering thought forces us to see the solid world around us as precarious, a thin crust over an abyss of deeper possibilities. The stability of everything we hold real is not guaranteed. It is merely a statistical accident, a temporary reprieve, and that uncertainty invites us to ask whether we can ever truly trust the ground beneath our feet, or whether the universe is always just one quantum fluctuation away from becoming something else entirely. Something is pulling entire clusters of galaxies toward an invisible target. Astronomers first noticed this strange motion in the late 2000s when they analyzed data from the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite that mapped the faint afterglow of the Big Bang. They were studying the velocities of hundreds of galaxy clusters, and they found that these enormous structures, each containing hundreds of galaxies, were all streaming in roughly the same direction at speeds of around 2 million miles per hour. This coherent flow, now called dark flow, does not fit the standard cosmological model. In the universe we understand, matter is distributed evenly on the largest scales. Galaxies and clusters move mostly under the influence of local gravity, and those motions should be random, cancelling out when averaged over the whole sky. No preferred direction should exist, yet dark flow suggests there is a large-scale bulk motion, a cosmic current that points toward a specific region of the sky, near the constellations of Centaurus and Hydra. The most troubling part is that the source of this pull lies far beyond the reach of our telescopes. The galaxy clusters we see are moving as if they are being gravitationally attracted by something outside the observable universe, a region of space we can never directly observe because its light has not had time to reach us. If true, this would violate a key assumption of cosmology called the cosmological principle, which states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction and from every location. Dark flow challenges that assumption head-on. It implies that the observable universe is not a representative sample of the whole. There might be immense structures or concentrations of matter just beyond our horizon that are tugging on everything we can see. What could that be? One possibility is a massive supercluster or a giant void, but such structures would have to be enormous to produce the observed pull across billions of light years. Another idea is more speculative. Perhaps dark flow arises from gravitational influences in a neighboring universe within a multiverse, where our cosmic bubble is being drawn toward a denser pocket of reality. Some theorists have even linked it to the concept of space-time shear, a distortion that might have been imprinted during inflation. The data itself remains controversial. Some later analyses of newer observations from the Planck satellite did not confirm the original dark flow signal, suggesting it might be a systematic error in the measurements. But other researchers still see a faint but persistent anomaly. The question is far from settled. If dark flow is real, it would mean that our entire observable cosmos is moving, flowing like a leaf on a river toward a destination we cannot see. That would force us to rethink the size and structure of the larger reality in which we are embedded. Our little bubble of space might not be isolated or typical. It could be part of a much larger landscape, one where the forces that shape it extend far beyond the limits of our vision. And that uncertainty, the possibility that the universe we map is not the whole story, leaves us with a haunting reminder of how small our vantage point truly is. A strange pattern in the oldest light in the universe points toward an impossible axis. This light is the cosmic microwave background, a faint glow that fills all of space, a relic from just 380,000 years after the Big Bang. When astronomers map this radiation, they expect to see tiny fluctuations, random hot and cold spots that are distributed evenly across the sky, like static on an old television. That randomness is a cornerstone of the standard cosmological model called lambda cold dark matter. It assumes that on the largest scales, the universe looks the same in every direction. But when researchers analyzed the data from the Wilkinson microwave anisotropy probe in the early 2000s, they found something deeply unsettling. The largest patterns in that background, specifically the quadrupole and the octupole, the lowest order of fluctuations, are not randomly oriented. They are aligned with each other along a specific direction in the sky, an axis that cuts through the solar system and points toward the constellations of Virgo and Leo. This alignment appears to violate the principle of isotropy, the idea that no direction is special. If the universe is truly isotropic, then those largest patterns should be pointing every which way, not lining up like soldiers on a march. The anomaly was so striking and so puzzling that cosmologists gave it a provocative name, the Axis of Evil. The name is playful, but the problem it represents is serious. If this alignment is real, it means our observable universe has a preferred direction, a cosmic arrow that contradicts the very foundations of modern cosmology. The standard model relies on the assumption that on the biggest scales, matter and energy are smoothly distributed, but an aligned axis suggests that there is something lopsided about the universe we live in. It could be a sign that our patch of space is not a fair sample of the whole. Perhaps there is a gigantic structure, a supervoid or a supercluster, that is distorting the microwave background on these largest scales. Or it could be something far more exotic, such as a signature from a previous cosmic cycle or a leftover from a period of anisotropic inflation, a time when space expanded at different rates in different directions. But before jumping to revolutionary conclusions, scientists first had to rule out the most mundane explanation: foreground contamination. Our own galaxy, the Milky Way, emits microwave radiation that can mix with the cosmic signal. Even after careful subtraction, subtle remnants might linger, and those remnants could mimic an alignment. Researchers have spent years refining their models of galactic emission, testing different subtraction methods, and even using data from the Planck satellite, which mapped the sky with higher resolution and sensitivity. The results have been frustratingly ambiguous. Some analyses suggest that after the best possible foreground removal, the alignment weakens but does not disappear. Others argue that it is likely just a statistical fluke, a rare fluctuation that is not as improbable as it first appears. The debate continues, but the very existence of this anomaly, even if it turns out to be a cosmic coincidence, has pushed cosmologists to ask deeper questions. Could the universe on the largest scales be far more complex than our current models allow? Might there be structures or forces that we have not yet accounted for? That is the tantalizing power of small discrepancies. They are the cracks where revolutionary ideas can take root. And the Axis of Evil is a perfect example of how a tiny bump in the data, a pattern that should not exist, can force us to re-examine the very assumptions that underpin our entire picture of reality. Our galaxy is being dragged across the cosmos by an invisible hand. The Milky Way, along with our entire local group of galaxies, is moving at roughly 2 million kilometers per hour toward a mysterious point in the constellation of Norma. Astronomers call this point the Great Attractor. It is a gravitational anomaly, a vast concentration of mass that pulls everything around it despite the universe's relentless expansion. You might think that the expansion of space, the force that pushes galaxies apart, would overwhelm any local attraction. But over distances of a few 100 million light-years, gravity still wins. The Great Attractor contains the mass of tens of thousands of galaxies, perhaps 100 quadrillion times the mass of our Sun, yet we cannot see it directly. The reason is the zone of avoidance, a dusty band that hides the center of our own galaxy from our view. The Great Attractor lies right behind that band, buried in the thickest part of the Milky Way's disk. Visible light cannot penetrate the dust and gas, so for decades this region remained a blank spot on our maps, astronomers had to use other wavelengths like X-rays and radio waves to peer through the haze. What they found was a tangled web of galaxy clusters, most notably the Norma cluster, which sits at the heart of the Great Attractor, but even that is not the whole story. Behind the Great Attractor, farther away and even more massive, lies the Shapley supercluster, a colossal chain of galaxy clusters spanning over 400 million light-years. Some researchers believe it is the true source of the pull, that the Great Attractor itself is just being drawn toward Shapley. Our local group is like a leaf caught in a stream that flows toward a waterfall, and that waterfall is the Great Attractor, but the stream itself is fed by an even larger current from the Shapley supercluster. This whole pattern challenges a key assumption of modern cosmology, that on the largest scales, the universe is smooth and uniform. The standard model of cosmology, called lambda cold dark matter, predicts that on scales above a few hundred million light-years, matter is distributed almost evenly, with no preferred direction or giant flows. Yet the Great Attractor and the Greater Shapley flow suggest that there are coherent currents spanning over 1 billion light-years, an entire hemisphere of the sky streaming in one direction. This is not a minor anomaly. It hints that the cosmic web, the structure of filaments and voids that makes up the large-scale universe, may be far more organized and less random than our models allow. If these flows continue across even larger scales, it could mean that the cosmological principle itself, the bedrock of our understanding, is only an approximation. The universe might have a kind of texture, a hidden topology that we are only beginning to glimpse. The Great Attractor is not a single object but a symptom, a gravitational knot in a much larger tapestry. And every time we peel back another layer, we find that the knot is tied to something bigger. What lies beyond the Shapley supercluster? Could there be an even larger attractor, a structure so vast that it governs the motion of everything we can observe? That question leads directly into one of the most controversial ideas in modern cosmology, the possibility that the entire observable universe is part of a much larger flow, a dark stream that connects our local patch to something beyond the horizon. Dark matter has never been directly detected, and some physicists believe we may not need it at all. Instead, they propose that gravity itself behaves differently than we have assumed for centuries. This idea is called modified Newtonian dynamics, or MOND for short. It was first suggested in the early 1980s by the Israeli physicist Mordechai Milgram, who noticed something puzzling about the rotation of galaxies. When astronomers measure the speeds of stars in the outer regions of a spiral galaxy, they find that those stars are moving much faster than they should be, based on the visible matter alone. In Newton's law of gravity, the farther a star is from the galactic center, the slower its orbit should be, just like the outer planets in our solar system move more slowly than the inner ones. But in galaxies, the outer stars orbit at nearly the same speed as the inner ones, a flat rotation curve that defies Newtonian predictions. The standard explanation is that an invisible halo of dark matter surrounds each galaxy, providing the extra gravity needed to keep those fast-moving stars from flying away. But Milgram noticed something else. The discrepancy only appears when the gravitational acceleration falls below a very specific threshold, roughly 1/10,000,000th of the acceleration you feel at Earth's surface. At accelerations above that threshold, Newton's laws work perfectly. Below it, gravity seems to strengthen, as if it refuses to fade away as quickly as expected. Milgram proposed that instead of adding invisible mass, we should modify the law of gravity itself. In his formulation, when accelerations are extremely weak, the gravitational force falls off more slowly than the standard inverse square law. This single change, with just one new constant, could predict the flat rotation curves of over 100 galaxies without invoking any unseen matter. That was a stunning success. MOND made specific, testable predictions about the relationship between a galaxy's brightness and its rotation speed. a relationship known as the Tully-Fisher relation, and it matched observations incredibly well, often better than dark matter models. It also explained the dynamics of dwarf galaxies and certain aspects of galaxy formation. Yet for all its elegance at galactic scales, MOND runs into serious trouble when we look at larger systems like clusters of galaxies. In clusters, the observed gravitational effects are far stronger than even MOND can account for, requiring some form of dark matter to fill the gap. Even more damning, MOND struggles to explain the cosmic microwave background, the ancient light that carries the imprint of the early universe. The detailed pattern of fluctuations in that radiation agrees remarkably well with a universe dominated by dark matter, and MOND simply cannot reproduce those patterns without adding dark matter back in. Efforts to make MOND work within the framework of Einstein's general relativity have been only partially successful. General relativity is an exquisitely tested theory, and any modification to gravity must reproduce everything it does correctly, from the precession of Mercury's orbit to the bending of light by the Sun. Several relativistic versions of MOND have been proposed, such as tensor vector scalar gravity, but they introduce new fields and parameters that reduce their simplicity. The result is a tension that remains unresolved. Dark matter remains the dominant explanation because it fits a much wider range of observations, from the smallest dwarf galaxies to the largest cosmic scales. But MOND refuses to die precisely because it predicts galactic rotation curves so naturally without any free parameters. It pushes us to ask a fundamental question: is the universe filled with an invisible substance, or is our understanding of gravity incomplete? Both answers are profound. If dark matter is real, then most of the universe's mass is something we have never seen, something that barely interacts with light. If MOND is correct, then gravity is not the fixed law we thought it was, and the very force that shapes the cosmos can change its behavior depending on the scale. Either way, the mystery forces us to re-examine the foundation of physics. And as we will see, this is not the only idea that challenges the nature of gravity itself. Gravity might not be the fundamental force we always thought it was. For centuries we have treated it as one of nature's four basic pillars, as real and irreducible as electromagnetism. But a growing number of physicists, led most prominently by the Dutch theorist Erik Verland, argue that gravity is not fundamental at all. It is an emergent phenomenon, a kind of illusion that arises from the statistical behavior of countless microscopic building blocks, much like the way temperature emerges from the random motion of atoms. You cannot point to a single atom and say it has temperature. Temperature is a collective property. In Verland's view, gravity is the same kind of collective effect, rooted in something even deeper: entropy. Entropy is a measure of disorder, or the number of ways a system can be arranged. The second law of thermodynamics says that in any closed system, entropy always increases. Now, what does that have to do with gravity? The connection came from black holes. In the 1970s, physicists discovered that black holes have an entropy proportional to the surface area of their event horizons. This was startling because entropy usually scales with volume, not area. It suggested that the information content of a black hole is stored on its two-dimensional surface, a concept that later grew into the holographic principle. Verland took that idea and ran with it. He proposed that gravity itself is nothing more than an entropic force. Imagine a tiny particle sitting near a surface that holds information about the location of other particles. As that particle moves, it changes the amount of information stored on the surface, and that change in information corresponds to a change in entropy. The universe, seeking to maximize entropy, naturally pushes the particle toward the surface, and we experience that push as gravity. It is a bit like the way a stretched rubber band snaps back. The band does not have an intrinsic force. The force emerges because the system is trying to reach a state of lower energy and higher entropy. Under this view, the curvature of spacetime predicted by Einstein is not the cause of gravity but a consequence of a deeper informational structure. This is a radical shift. It means that space and time are not the stage on which physics plays out. They are themselves players, emergent from a more fundamental layer of quantum bits of information. And here is where it gets even more interesting. Verland argues that the same logic can explain two of the biggest mysteries in cosmology: dark matter and dark energy. Dark matter is the invisible mass we infer from galactic rotation curves, but we have never detected a particle of it. Verland suggests that what we call dark matter is actually an extra gravitational pull that emerges from the entropy of the universe on galactic scales. In his model, the dark matter effect is not a substance but a side effect of the way information is distributed in space. Similarly, dark energy, the mysterious force accelerating the expansion of the universe, could be an emergent phenomenon tied to the cosmic horizon, the boundary of our observable universe. As the universe expands, the horizon grows and the amount of information encoded on it changes, producing a repulsive force that we interpret as dark energy. These ideas are still controversial. Many physicists are skeptical because Verland's models have difficulty matching all the data, especially the detailed patterns in the cosmic microwave background and the precise dynamics of galaxy clusters. But the elegance of the theory, its roots in deep principles like entropy and the holographic principle, have earned it serious attention. It offers a unified framework where gravity, dark matter, and dark energy all share the same origin: the statistical tendency of information to spread out. If Verland is right, then the fabric of the cosmos is not a smooth sheet of spacetime but a buzzing network of quantum bits, and the forces we feel are just the macroscopic result of that microscopic hustle. That naturally raises the question: if dark energy is an emergent illusion, what does that say about the accelerating expansion of the universe? Perhaps the vacuum is not truly repulsive. Perhaps the expansion is not accelerating at all, and what we interpret as dark energy is something else entirely, something that points toward an even deeper revision of the standard model. What if dark energy is not a constant but a phantom that grows stronger over time? For decades, the standard model of cosmology assumed that dark energy behaves like a cosmological constant, a fixed repulsive force that fills space evenly and never changes. But some physicists are exploring a more unsettling possibility. Dark energy might be what they call a phantom field, an exotic form of energy whose properties push it beyond the boundaries of ordinary physics. In the equations, this is described by a number called the equation of state, often labeled W. For a cosmological constant, W equals exactly -1. That means the repulsive force stays perfectly steady. But if W drops below -1, if it becomes, say, -1.2 or -1.5, then the energy density of the phantom field does not stay constant. It increases over time, and as it increases, its repulsive effect grows stronger, accelerating the expansion of the universe even faster. This leads to a scenario that cosmologists call the Big Rip. In a Big Rip, the accelerating expansion does not just push galaxies apart. It eventually overcomes every force that holds matter together. First, galaxy clusters dissolve as the repulsion tears them apart. Then individual galaxies unravel, their stars scattered into lonely orbits. Then solar systems break free from their stars. Then planets themselves are pulled apart. Then atoms, the very bonds that hold electrons to nuclei, are stretched and broken. And finally, space-time itself, the fabric of reality, is ripped into disconnected fragments. The timeline depends on exactly how far below -1 W is. If W is -1.001, the Big Rip might not happen for hundreds of billions of years. But if W is significantly lower, the end could come in just a few tens of billions of years. That is still far beyond human timescales, but it is a finite future, a definitive end to all structure in the universe. This idea is not just a theoretical curiosity. Observational data from supernova, the cosmic microwave background, and the large-scale structure of galaxies have placed constraints on W. The most precise measurements from the Planck satellite and from surveys of distant supernova suggest that W is very close to -1, with an uncertainty of about plus or minus 0.04. That means the data are consistent with W being exactly -1, but they also allow W to be slightly less than -1. The error bars have not ruled out a phantom field. In fact, some analyses of particular datasets have even hinted at W being just a tiny bit below -1, though the evidence is far from strong. So phantom energy remains a serious possibility, one that challenges the very nature of dark energy. If it is real, then the cosmological constant is not the final answer. There is something more dynamic at work, something that is slowly winding up the repulsive force like a spring being coiled, and that raises deeper questions. What kind of field could have such an extreme equation of state? How does it fit into quantum field theory, which usually forbids such behavior? Some theorists have tried to build phantom field models using exotic scalar fields with negative kinetic energy, ghost-like fields that violate certain energy conditions. Such fields are notoriously unstable, and they often produce unwanted side effects like faster-than-light propagation or violations of causality. Yet a few models manage to stabilize them within a limited energy range, making them mathematically possible even if physically distasteful. The fact remains that observations have not slammed the door on phantom energy. It sits at the edge of what we can measure, a speculative but plausible explanation for the acceleration of the universe. And if it is the correct explanation, then the cosmos is not heading toward a gradual heat death or a slow fade. It is heading toward a violent end, a crisis in which the very geometry of space unravels. That tension between the comforting idea of a constant dark energy and the unsettling phantom field is part of what makes cosmology so compelling. The answers are not settled. The data keep us guessing, and every new measurement of supernova or of the cosmic microwave background brings us closer to knowing whether dark energy is a steady force or a rising threat. For now, the phantom field remains a possibility, a strange and serious hypothesis that forces us to consider the ultimate fate of everything we know. Not every cosmic fate ends in a violent rip. Some cosmologists envision a different end, one where the universe's expansion eventually slows, stops, and reverses, pulling everything back together in a final crushing collapse. This is the Big Crunch, the mirror image of the Big Bang. In this scenario, the universe contains enough matter and energy for gravity to overcome the repulsive push of dark energy. The expansion reverses, galaxies fall toward each other at ever-increasing speeds. The cosmic web of filaments and voids begins to compress, and all the matter in the cosmos is steadily squeezed into a smaller and smaller volume. Temperatures rise, stars are torn apart by extreme tidal forces, atoms themselves break down, and eventually, the entire observable universe is crushed into an infinitesimal point, a singularity of infinite density and temperature. But the story does not have to end there. When you run the equations of general relativity forward to that singularity, they break down. That is where quantum gravity steps in. In the extreme conditions just before the singularity, the laws of physics must shift from the smooth, continuous picture of spacetime into a discrete, quantum mechanical description. In that regime, the singularity might be avoided altogether. Instead of a dead end, the collapse could become a bounce. The universe, at its smallest possible size, experiences a quantum recoil, a sort of cosmic spring that pushes it back outward in a new Big Bang. This is the Big Bounce, a cyclic model where each universe gives birth to the next, and each cycle lasts trillions of years. There is no absolute beginning and no final end. The cosmos simply breathes in and out, expanding and contracting in an endless rhythm. One of the most thought-provoking versions of this idea comes from the physicist Roger Penrose. He calls it conformal cyclic cosmology. Penrose argues that near the end of a universe, when it has expanded to an almost empty, cold, and flat state, something strange happens. Because the universe is so uniform at that point, the difference between past and future becomes meaningless. Time essentially loses its arrow. In that extreme condition, the geometry of the universe can be stretched or conformally scaled to match the geometry of a new Big Bang. In other words, the infinite future of one universe becomes the beginning of the next. There is no collapse, no crushing, only a smooth transition from one cosmic eon to the next. Penrose points to a possible marker of this cycle hidden in the oldest light we can see. The cosmic microwave background, he suggests, might bear the imprints of events that happened in the previous eon. Specifically, he believes that the concentric rings of slightly different temperature seen in the microwave background, called Hawking points, are actually the signatures of supermassive black holes from the previous universe, slowly evaporating through Hawking radiation. The radiation leaves faint, circular imprints in the sky, like ripples on a pond that carry information from a time before our Big Bang. Most cosmologists remain skeptical of this claim, arguing that the patterns are likely statistical noise or foreground contamination. But the idea itself is tantalizing. It offers a way to test a theory of endless cycles using real observational data. If Penrose is right, then the universe we see is not unique. It is just one chapter in an infinite book, endlessly written and rewritten. There was no first moment, no beginning of time. The Big Bang was not the start of everything but a transition, a bridge from one cosmic age to the next. This view challenges the very notion of a single, linear history. It suggests that time itself may be cyclical, that the events of our universe will eventually repeat in some transformed way. And that forces us to ask a deeper question. If the universe has no ultimate origin and no final destination, if it simply spins through an endless series of births and deaths, then what does that say about our place within it? The search for a beginning may be an artifact of our own limited perspective, a need to anchor our story in a moment of creation, but the cosmos, it seems, might not share that need. It might be perfectly comfortable without a first page, existing forever in a cycle of transformation that leaves behind only subtle echoes, ripples in the fabric of reality that we are only just beginning to learn how to read. A black hole that runs in reverse would spew out matter instead of swallowing it. This hypothetical object is called a white hole, and it is the exact mathematical opposite of a black hole. In Einstein's equations of general relativity, a black hole is a region where gravity is so intense that nothing, not even light, can escape. The defining feature is the event horizon, a one-way boundary. Anything that crosses that horizon is trapped forever, but the equations are time-symmetric. If you take a solution for a black hole and reverse the direction of time, you get a white hole. Instead of an inescapable trap, you have an inescapable fountain. Matter and energy pour out from a white hole, but nothing can ever enter it. The event horizon now acts as a one-way barrier in the opposite direction. You could approach a white hole, but you could never cross its boundary because that would require traveling backward in time relative to the internal geometry. These objects are mathematically valid solutions to the equations of general relativity, but there is a huge catch. White holes are violently unstable. The moment any particle from the outside universe approaches the white hole, that particle's tiny gravitational influence perturbs the structure, and the white hole collapses into a black hole in an instant. In a universe filled with matter and radiation, even a perfect white hole would not survive for more than a fraction of a second. That is why astronomers have never found evidence for one, and why most physicists consider them a mathematical curiosity rather than a real phenomenon. Yet the idea persists in popular culture and in theoretical discussions because it opens a door to an even more tantalizing concept: wormholes. A wormhole is a tunnel through space-time, a shortcut that connects two distant points. In the mathematics of general relativity, wormholes emerge naturally from solutions that combine a black hole and a white hole. Imagine a black hole that does not end in a singularity, but instead connects through a throat to a white hole in another region of the universe. That throat is a wormhole. You could enter the black hole end, travel through the tunnel, and emerge from the white hole end, potentially millions of light years away or even in a different universe altogether. The trouble is that the same instability that plagues white holes also threatens wormholes. The throat of a wormhole, the narrowest point of the tunnel, is under enormous gravitational stress. To keep it from collapsing under its own weight, you would need something with negative energy or negative mass. This is called exotic matter. Exotic matter is not the stuff of everyday experience. It is a hypothetical form of matter that violates certain energy conditions in general relativity. It would have repulsive gravity, pushing things away instead of pulling them together. No such substance has ever been observed, but quantum field theory does allow for brief, tiny amounts of negative energy in certain quantum fluctuations. Sustaining a wormhole big enough for a spaceship to pass through would require enormous quantities of this exotic matter, far beyond anything nature seems to provide. So wormholes remain purely theoretical, but they are not impossible. They do not violate any known laws of physics. They simply require conditions that we have never seen and do not know how to produce. That is what makes them so fascinating for science fiction and for serious theoretical research. A stable wormhole could act as a time machine. If one mouth of the wormhole is accelerated to near light speed and then brought back, time dilation would cause that mouth to age more slowly than the stationary mouth. Entering the younger mouth would allow you to emerge from the older mouth at an earlier time, effectively traveling into the past. This creates the same paradoxes that plague all time travel scenarios, like the famous grandfather paradox, but the math does not forbid it. General relativity allows for closed timelike curves, loops in spacetime where cause and effect become tangled. Whether the universe actually permits such loops is an open question. Some physicists believe that quantum effects would prevent time travel by creating feedback loops that destroy the wormhole before it can be used. Others think that the paradoxes might be resolved by the many worlds interpretation, where changing the past simply spawns a new timeline. The debate is far from settled. White holes and wormholes push the boundaries of what we consider possible within the framework of gravity. They are ghosts in the equations, objects that could exist but probably do not, and yet they force us to confront the strange implications of Einstein's theory. If time can flow in both directions through a tunnel in spacetime, then our simple picture of past and future might be just a local illusion. And that illusion becomes even more fragile when we realize that the very fabric of the universe might be woven from the smallest possible threads of reality. Threads that behave in ways our intuition was never designed to grasp. Time travel emerges from the same equations that predict black holes and wormholes. In the late 1940s, the mathematician Kurt Gödel discovered a solution to Einstein's field equations that described a rotating universe. In this universe, the entire cosmos spins on its axis, and that rotation drags spacetime along with it. If you travel far enough in the right direction, you can loop back to your own past, tracing a closed path in time called a closed timelike curve. Gödel's solution was purely theoretical. Our own universe does not rotate in that way, but it proved that general relativity does not automatically forbid time travel. The equations allow it under certain conditions. A more practical proposal came decades later from the physicist Frank Tipler. He imagined an infinitely long, dense cylinder spinning at incredible speeds. The rotation of the cylinder would twist spacetime around it, creating a closed loop that could carry a spaceship backward in time if it flew a precise trajectory. Tipler's cylinder is just as theoretical as Gödel's universe, requiring materials and energies far beyond anything we can build. Yet both solutions share a powerful implication. The laws of gravity alone do not prohibit time travel. They simply make it extraordinarily difficult, but if such loops could exist, they create a logical nightmare known as the grandfather paradox. You travel back in time and prevent your own grandfather from meeting your grandmother. Then you are never born, so you cannot travel back in time, so the event never happens. Causality unravels. The universe would seem to forbid such contradictions. One attempt to resolve this is the Novikov self-consistency principle, named after the Russian physicist Igor Novikov. It states that any action you take in the past must already be part of the timeline you came from. You cannot change the past, only fulfill it. If you try to kill your grandfather, something will stop you: a jammed gun, a sudden illness, a missed shot. The timeline is fixed. Your actions are constrained to produce the exact same future you remember. This principle preserves causality but eliminates free will in a very specific way. You could go back in time, but only to do things that already happened. You are a passenger on a predetermined track, yet quantum mechanics offers a different perspective. At the quantum level, particles exist in superpositions of multiple states, and time may not be as rigid as it seems. Some interpretations, like the many worlds view, suggest that time travel into the past would simply split the universe into two branches. In one branch, you kill your grandfather, creating a paradox-free timeline where you never existed, but where you did exist in a different branch. In the other branch, everything proceeds normally. The paradox disappears because there is no single timeline to violate. Other quantum approaches, like the post-selected teleportation model, show that closed timelike curves can exist without contradictions if you allow for probabilistic outcomes and self-consistent quantum states. The equations work out, but they often require extreme fine-tuning or exotic conditions. So far, no experiment has ever detected a closed timelike curve. All evidence points to a universe where cause always precedes effect, but the theoretical door remains open, just a crack, and that crack forces us to ask whether time is as fundamental as we believe, or whether it is a property that can be bent, twisted, and even looped back on itself. The answer may lie not in gravity alone, but in the strange rules of the quantum world, where the very concept of before and after might be just a convenient approximation. The most controversial solution to the quantum puzzle denies that randomness exists at all. Superdeterminism takes the correlations we observe between particles and traces them back to a single cause, a deep predetermination that was set in motion at the very beginning of the universe. According to this interpretation, the choice of which measurement to make and the outcome of that measurement are not independent events. They are linked from the Big Bang, woven together by the same initial conditions that shaped every particle and every observer. This idea directly challenges a cornerstone of experimental physics known as statistical independence. In standard quantum mechanics, when you run a Bell test, you assume that the experimenter choice of which setting to use is completely independent from the state of the particles being measured. That assumption is what allows Bell's theorem to prove that local hidden variable theories cannot reproduce quantum predictions. But superdeterminism simply rejects that assumption. It says the experimenter's choice and the particle's state are correlated from the outset, not because of any signal traveling faster than light, but because both are products of the same cosmic starting point. If that is true, then the Bell test results that seem to rule out local hidden variables are actually consistent with a perfectly local theory, as long as the initial conditions are conspiratorial enough. Physicists call this kind of conspiracy superdeterminism, and most find it deeply unpalatable. The reason is that it essentially removes the notion of free will from the equation. If every measurement setting and every outcome are predetermined since the beginning of time, then the experimenter's choice is an illusion. You might think you decided to rotate a detector by 10 degrees, but that decision was already fixed when the universe was a fraction of a second old. This is not a violation of any known physical law. It is logically consistent. The universe could be exactly like this, with every event perfectly correlated across cosmic distances and cosmic times. But it feels like an intellectual dead end. It offers no new predictions, no way to test it against other interpretations. It simply explains away the strange correlations of quantum mechanics by positing an underlying cosmic conspiracy. That is why most physicists resist it. They prefer interpretations like many worlds or Boltzmann mechanics that preserve the independence of experimental choices. Yet superdeterminism remains a logical alternative, one that forces us to confront a deeply uncomfortable question. How much of what we call free choice is actually an illusion woven into the fabric of reality from the very first moment? That question leads directly into theories that abandon free will altogether, not as a philosophical position but as a necessary consequence of how the universe operates. The most controversial solution to the quantum puzzle denies that randomness exists at all. Superdeterminism takes the correlations we observe between particles and traces them back to a single cause, a deep predetermination that was set in motion at the very beginning of the universe. According to this interpretation, the choice of which measurement to make and the outcome of that measurement are not independent events. They are linked from the Big Bang, woven together by the same initial conditions that shaped every particle and every observer. This idea directly challenges a cornerstone of experimental physics known as statistical independence. In standard quantum mechanics, when you run a Bell test, you assume that the experimenter choice of which setting to use is completely independent from the state of the particles being measured. That assumption is what allows Bell's theorem to prove that local hidden variable theories cannot reproduce quantum predictions, but superdeterminism simply rejects that assumption. It says the experimenter's choice and the particle's state are correlated from the outset, not because of any signal traveling faster than light, but because both are products of the same cosmic starting point. If that is true, then the Bell test results that seem to rule out local hidden variables are actually consistent with a perfectly local theory, as long as the initial conditions are conspiratorial enough. Physicists call this kind of conspiracy superdeterminism, and most find it deeply unpalatable. The reason is that it essentially removes the notion of free will from the equation. If every measurement setting and every outcome are predetermined since the beginning of time, then the experimenter's choice is an illusion. You might think you decided to rotate a detector by 10 degrees, but that decision was already fixed when the universe was a fraction of a second old. This is not a violation of any known physical law. It is logically consistent. The universe could be exactly like this, with every event perfectly correlated across cosmic distances and cosmic times. But it feels like an intellectual dead end. It offers no new predictions, no way to test it against other interpretations. It simply explains away the strange correlations of quantum mechanics by positing an underlying cosmic conspiracy. That is why most physicists resist it. They prefer interpretations like many worlds or Boltzmann mechanics that preserve the independence of experimental choices. Yet superdeterminism remains a logical alternative, one that forces us to confront a deeply uncomfortable question. How much of what we call free choice is actually an illusion woven into the fabric of reality from the very first moment? That question leads directly into theories that abandon free will altogether, not as a philosophical position but as a necessary consequence of how the universe operates. The mind may not be a product of the brain at all but a fundamental player woven into the fabric of reality. This is the central claim of the orchestrated objective reduction theory, or Orch-OR for short, a bold hypothesis developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness does not emerge from the firing of neurons alone, but from quantum processes taking place deep inside the brain's smallest structures. Inside every neuron are tiny protein filaments called microtubules. These hollow tubes, about 25 nanometers wide, form the cell's internal skeleton and help transport materials. But Penrose and Hameroff argue that microtubules do more than just structural work. They believe these microstructures can sustain delicate quantum states, like the superposition of two possible configurations at the same time. Under the Orch-OR model, each moment of conscious experience corresponds to a specific quantum event. When a superposition of microtubule states reaches a certain threshold, it collapses in a way that is not random but orchestrated by the geometry of spacetime itself. This collapse, which Penrose calls objective reduction, is the fundamental tick of consciousness, a pulse of non-computable awareness. The theory ties together quantum mechanics, the structure of the brain, and the deepest properties of the cosmos. If correct, it would mean that consciousness is not an accidental byproduct of complex computation. It is a bridge between the quantum world and the classical one, a bridge built from the geometry of spacetime. But the idea faces a major obstacle: the warm, wet, chaotic environment inside a living brain. Quantum effects are notoriously fragile. Superpositions typically last only fractions of a second in isolation, and in a warm biological system like a neuron, they should decohere almost instantly, destroyed by collisions with surrounding molecules. Critics argue that the timescales required for Orch-OR are far too long for such conditions to support any meaningful quantum behavior. Hameroff and others have responded by pointing to evidence of quantum coherence in biological systems like photosynthesis and bird navigation, where quantum effects survive in warm, noisy environments. They also note that microtubules are arranged in an ordered, crystalline lattice that might protect quantum states from decoherence, much like a crystal preserves a precise pattern. Recent experiments have even suggested that certain anesthetics which disrupt consciousness also dampen quantum vibrations in microtubules, a hint that the link may be real. The debate remains fierce, but the implications of the theory are staggering. If consciousness emerges from quantum processes tied to the fundamental structure of spacetime, then the mind is not just a local phenomenon inside your skull. It is a window into the deepest layers of reality, a part of the universe's basic fabric rather than a latecomer. That shifts the ancient question of mind and body from a problem of biology to a question about the nature of existence itself. Perhaps consciousness is not something that arises when matter reaches a certain complexity. Perhaps it is a fundamental property of the universe, as basic as mass or charge, waiting to be discovered in places we have only begun to explore. John Wheeler proposed that observers actively shape reality. He called this the participatory anthropic principle. For Wheeler, the act of observation was not a passive recording of events. It was a necessary step that retroactively brings those events into existence. This radical idea grew out of a simple question. If quantum mechanics says that a particle exists in multiple states until it is measured, then what exactly happens when we measure it? Wheeler argued that the observer does not just discover a pre-existing fact. The observer, by choosing what to measure and how to measure it, helps decide which past actually happened. The delayed choice quantum eraser experiment provides a stunning demonstration of this. In a standard double-slit experiment, a photon passes through two slits and creates an interference pattern showing wave behavior. But if you place a detector at each slit to determine which path the photon took, the interference disappears and the photon behaves like a particle. The twist comes when you delay that decision. In a delayed choice eraser, the photon is sent through the slits, and its which path information is encoded in an entangled partner photon. The experimenter can then choose to erase that which path information after the photon has already passed through the slits. If the information is erased, the interference pattern reappears. If it is not erased, the pattern stays particle-like. The crucial point is that the choice to erase or not is made after the photon has already traveled. Yet that later decision retroactively determines whether the photon behaved as a wave or a particle. The past is not fixed until the future measurement is completed. This experiment does not require a conscious observer at the moment of choice. The erasing process can be automated, but it does show that the act of measurement, the acquisition of information, plays a fundamental role in defining what is real. Wheeler took this to its logical conclusion. If the universe at its most basic level is a collection of quantum events, then those events are not fully real until they are observed. And since the universe has been around for billions of years before any life emerged, the question becomes, who or what performed the first observation? Wheeler offered a startling answer. The universe itself, through the emergence of conscious observers, loops back to observe its own past. In a sense, the Big Bang is not a beginning that happened long ago. It is an event that is being brought into existence right now by the observations we make today. The universe is not a static stage waiting for actors to appear. It is a dynamic, participatory process where observers are not spectators but co-creators. This idea has profound philosophical implications. It suggests that reality does not have a single, independent existence. Instead, it is a product of the relationship between the observer and the observed. Without conscious observers, the universe would remain a haze of quantum possibilities, never settling into a definite state. That does not mean the universe depends on human beings specifically. It means that any information-gathering system, any interaction that records a result, plays a participatory role. But Wheeler emphasized the role of consciousness because of the unique way we reflect on our own existence. He once said that we are not just observers but participants in a universe that we help to create through our choices. This participatory view naturally leads to a cosmic loop. If the universe requires observers to exist, and those observers are products of the universe, then the system is self-referential. The universe bootstraps itself into being through the emergence of minds that then look back and complete the act of creation. This is not a paradox. It is a closed causal loop, a kind of cosmic circuitry where the effect influences the cause. And that idea points toward the next theory, one that treats the entire universe as a self-excited circuit, a feedback loop of information and observation that generates reality from within itself. The same self-referential logic appears in a theory of light and time. It emerged from a collaboration between John Wheeler and his student Richard Feynman in the 1940s as they wrestled with an old puzzle in electromagnetism. When an electron accelerates, it emits electromagnetic radiation, and that radiation carries away energy, causing the electron to feel a recoil force called radiation reaction. If you solve Maxwell's equations in the standard way, you get only one kind of solution: retarded waves that travel forward in time from the source to an absorber. But the equations also permit another kind of solution: advanced waves that travel backward in time from the absorber to the source. Wheeler and Feynman took a radical step. They proposed that both kinds of waves are real. When an electron accelerates, it sends out both a retarded wave into the future and an advanced wave into the past. That advanced wave reaches other charged particles throughout the universe, and those particles respond by sending their own advanced and retarded waves back toward the original electron. The net effect of all these interactions, summed across every charged particle in the cosmos, produces the radiation reaction force. In this picture, the electron's motion is not determined by its own past alone. It is shaped by the entire future response of every other particle in the universe. The cosmos acts as a giant absorber, and the sum of all those future interactions determines what happens in the present. Causality is not a one-way street from past to future. It is a two-way conversation, a self-consistent loop where the future participates in shaping the past. Wheeler saw this as a model for the universe itself. If electromagnetic interactions could be understood as a closed loop of advanced and retarded signals, then perhaps the entire cosmos operates on the same principle. The universe does not have a beginning that causes everything after it. Instead, it is a self-excited circuit, a system that bootstraps itself into existence by being internally consistent from moment to moment. Every event in the universe is connected to every other event through a network of influences that travel both forward and backward in time. There is no first cause, no initial condition that sets everything in motion. The universe simply is because its own internal logic holds it together. This idea challenges our everyday notion of time as a linear arrow. If the future can influence the past in a self-consistent loop, then the distinction between cause and effect dissolves. An event is not caused by something that happened earlier. It is caused by the entire system, past and future together, arranged in a coherent pattern. That is exactly the structure of a block universe, where all moments exist simultaneously, and the flow of time is an illusion created by our limited perspective. In such a cosmos, the Big Bang is not a singular beginning. It is a necessary part of the loop, a boundary condition that emerges from the requirement of self-consistency rather than from a moment of creation. The universe asks no external permission to exist. It is its own reason for being, and that is the deepest mystery of all, a mystery that forces us to see the whole of reality as a single, timeless, self-generating circuit in which every part depends on every other part, including the observers who are trying to understand it. A collision between two invisible sheets of reality might have triggered our universe. This is the central idea of the ekpyrotic universe, a model developed by physicists Paul Steinhardt, Neil Turok, and others in the early 2000s. It begins with a concept from string theory called branes. In string theory, our familiar three dimensions of space plus time are just a slice of a higher dimensional cosmos. These slices, known as branes, are like vast, flat membranes floating in a 5- or 6-dimensional space called the bulk. In the ekpyrotic model, there are at least two such branes, each containing its own universe, separated by a tiny gap in the extra dimension. For eons, these branes sit quietly, drifting slowly toward each other due to a gentle attractive force. Then, eventually, they collide. The collision releases an enormous burst of energy, heating the branes to trillions of degrees and creating all the matter and radiation we see. This event is what we call the Big Bang, but unlike the standard Big Bang, which begins with a singularity where the laws of physics break down, the ekpyrotic collision is a smooth, controlled event. The branes are not infinitely dense points, they are extended sheets, and their collision is a physical process that can be described by known equations. This elegantly avoids the singularity problem that plagues standard cosmology. Another major advantage is that the ekpyrotic model naturally explains two puzzling features of our universe, its flatness and its homogeneity. In the standard inflationary model, these properties are attributed to a brief period of exponential expansion that smoothed out irregularities. But in the ekpyrotic scenario, the collision itself does the job. As the branes approach each other, the intervening space stretches in a specific way that drives the universe toward flatness and uniformity, all without the need for a mysterious inflation field. This is a different kind of smoothing mechanism, one rooted in the geometry of extra dimensions rather than in a hypothetical field. So how does it compare to inflation? Both theories solve many of the same problems, but they make different predictions. One key difference lies in the pattern of gravitational waves. Inflation predicts a specific spectrum of primordial gravitational waves, ripples in spacetime that would have left a faint imprint on the cosmic microwave background. The ekpyrotic model predicts a much weaker signal, almost undetectable by current experiments. This is a crucial test. If future observatories like the Laser Interferometer Space Antenna or advanced B-mode polarization searches find a clear gravitational wave background from the early universe, it would favor inflation. If the signal is absent or extremely faint, the ekpyrotic model becomes more attractive. There is also a difference in the nature of the initial fluctuations. In inflation, quantum fluctuations are amplified and stretched to cosmic scales, becoming the seeds for galaxies. In the ekpyrotic model, the fluctuations arise from quantum effects in the brane collision itself, and they have slightly different statistical properties. For instance, the ekpyrotic model predicts a small but measurable level of non-Gaussianity, a deviation from pure random noise that differs from the predictions of simple inflation models. Future galaxy surveys could reveal these differences, tipping the scales one way or the other. The ekpyrotic universe does not require a beginning of time. The branes have always existed, moving and colliding in an endless cycle. After each collision, the branes rebound, expand, and then slowly drift back together for another collision, producing a new Big Bang. This is a cyclic cosmology similar to the Big Bounce, but with the added structure of extra dimensions. It offers a picture of the cosmos that is eternal without a first moment and continuous without singularities. It ties the origins of our universe to processes happening in dimensions we cannot see, and it gives us a way to test those ideas with observations of the sky. As we move toward the final theory in this journey, the ekpyrotic model leaves us with a powerful reminder. The Big Bang may not have been a unique event, but just one beat in a cosmic rhythm that has played out before and will play out again forever. The universe will not last forever. Current observations point toward 3 possible endings, each more unsettling than the last, and each one depends on a single unknown, the true nature of dark energy. The first scenario is the Big Chill, also called heat death. If dark energy behaves like a cosmological constant, a steady repulsive force that never changes, then the expansion of space will continue forever, slowly accelerating. Galaxies will drift farther apart until the night sky becomes empty. Stars will burn out one by one, leaving behind cold cinders and black holes. Those black holes themselves will eventually evaporate through Hawking radiation, releasing a faint glow that fades into nothing. The universe will become a thin, cold soup of particles drifting in an ever-growing void. Temperature will approach absolute zero, and no further change will ever occur. Time itself will lose meaning because nothing will happen to mark its passage. The second scenario is the Big Rip. This fate requires dark energy to be something far more aggressive, a phantom field whose repulsive force grows stronger over time. In this case, the acceleration does not just push galaxies apart. It eventually overwhelms every force that holds matter together. First, galaxy clusters dissolve. Then galaxies unravel, then solar systems break apart, planets are torn from their stars, eventually atoms themselves are stretched and ripped apart, and finally space-time itself is torn into disconnected fragments. The timeline depends on how fast the phantom field strengthens, but if it is real, the end would come in a finite time, perhaps tens of billions of years from now, a definitive, violent conclusion. The third scenario is the Big Freeze. It resembles the Big Chill in many ways, but with a crucial difference. In this version, the expansion continues forever while the universe also loses all remaining energy gradients. Every particle decays into its lowest possible state. Protons, the building blocks of ordinary matter, may eventually decay, a process that has never been observed but is predicted by some grand unified theories. The universe becomes a featureless, frozen void where no structure remains, not even individual particles. All that is left is a cold, dark, eternal stillness, a state where entropy has reached its maximum and no further change is possible. Which of these 3 will be our reality? The answer hinges on the exact value of dark energy's equation of state, the number that measures how its repulsive force changes with time. Current measurements place this number very close to -1, the value for a constant dark energy, but the error bars still allow for values slightly above or below. The difference is tiny, but it determines whether the universe fades out slowly, rips apart violently, or freezes into an eternal silence. Each scenario challenges our understanding of time and existence in a different way. In the Big Chill, time becomes meaningless because nothing ever changes. In the Big Rip, time ends in a finite event. In the Big Freeze, time continues but without any meaningful events, a kind of eternity without content. Scientists are working to narrow down the true fate. Future missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will measure the expansion history of the universe with unprecedented precision. They will watch how galaxies move, how supernovas shine, and how the cosmic web grows, all to pin down that one number. The answer may come within our lifetimes, or it may take decades. But the question itself is one of the most profound humanity can ask. Not where we came from, but where we are going. And the answer will reshape how we think about our place in the cosmos, not just as observers of a grand story, but as beings who live in a universe that is still deciding its own fate. The search for that answer continues, and every new piece of data brings us closer to understanding whether our reality will end in a whisper, a scream, or a silent freeze. Mathematics is the language that makes these ideas possible. Before any experiment or observation, a bizarre theory often begins as a set of equations on a chalkboard, a piece of elegant mathematics that demands to be taken seriously. The fine-tuning argument for the multiverse, for example, springs directly from the numbers that govern our universe. When physicists calculate the strength of the strong nuclear force or the mass of the Higgs boson, they find values that seem impossibly precise for life to exist. The equations themselves offer no explanation for why those numbers are what they are, but they do allow for a vast landscape of possibilities. That mathematical openness is what gives the multiverse its first foothold, a logical structure that is internally consistent even if we cannot yet see the other universes. The same is true for the black hole information paradox. It emerged from Stephen Hawking's elegant application of quantum field theory to curved spacetime. The math showed that black holes radiate, and that radiation carries no information about what fell in. That result was so clean and so troubling that it forced physicists to reconsider the foundations of quantum mechanics and gravity. The equations did not lie, but they pointed to a contradiction. So researchers spent decades searching for a resolution, not because they had any direct evidence of information escaping, but because the math demanded that it must. In both cases, the theory stands on the strength of its internal logic long before any telescope or particle detector can confirm it. The holographic principle, the simulation hypothesis, the many worlds interpretation, each of them began as a mathematical insight, a solution to an equation that seemed too beautiful or too consistent to ignore. But beauty alone is not proof. Mathematics can describe an infinite number of possible worlds, but only one of them is the one we actually inhabit. That is where observation becomes the final judge. The equations of the ekpyrotic universe predict a specific pattern of gravitational waves. The mathematics of phantom dark energy predicts a finite end date for the universe. Those predictions can be tested. If future data matches the math, the theory gains credibility. If it does not, the theory, no matter how elegant, must be revised or discarded. This is the delicate balance of theoretical cosmology. The math opens the door, but the sky holds the key. And as telescopes grow more powerful and experiments become more precise, the line between speculation and science will be drawn not by the beauty of the equations, but by the stubborn facts of the cosmos. The next step, then, is to turn from the chalkboard to the instruments that can actually measure the universe, to see whether any of these bizarre ideas leave a trace in the light that reaches us from across the ages. That ancient light carries whispers that our most sensitive detectors struggle to hear. The cosmic microwave background, the faint echo of the Big Bang, is one of the most powerful tools we have for testing the bizarre theories we have explored. But its signals are subtle, buried in noise, and often just at the edge of what our instruments can resolve. Consider the anomalies we mentioned earlier, the axis of evil or the cold spot in the microwave sky. These features appear in the data, but their statistical significance is borderline. Are they real cosmological signatures or just random fluctuations? The same uncertainty haunts the rotation curves of galaxies, the very observation that led to the dark matter hypothesis. Astronomers have measured the speeds of stars in over 100 galaxies, and in every case the outer stars move faster than Newton's laws predict. That is a consistent, reliable anomaly, but it does not tell us what causes it. It could be dark matter or modified gravity or something else entirely. The data alone cannot distinguish between these possibilities without further clues. This is the fundamental challenge of experimental cosmology. Many of the theories we have discussed, the multiverse, the simulation hypothesis, the holographic principle, make predictions that are either too faint, too distant, or too subtle for current technology to confirm or refute. For example, if our universe is a hologram, there might be tiny deviations in the way gravity behaves at the smallest scales, but those deviations are far below the sensitivity of today's gravitational wave detectors. If we live in a multiverse, collisions between bubble universes might leave faint imprints in the cosmic microwave background, but those imprints would be vanishingly rare and hard to distinguish from ordinary noise. A lack of evidence does not mean a theory is wrong. It simply means the theory remains in the realm of speculation, waiting for a breakthrough in instrumentation or a lucky observation that tips the scales. Science progresses by systematically eliminating unlikely ideas, and many bizarre theories serve as inspiration for new detectors and missions. The search for primordial gravitational waves, for instance, was motivated in part by the predictions of inflation and the ekpyrotic model. Even though no definitive signal has been found yet, the search has pushed the boundaries of what we can measure, leading to new techniques and a deeper understanding of the early universe. In a very real sense, these ideas are not just flights of fancy. They are engines of discovery, forcing us to build better telescopes, more sensitive detectors, and more creative experiments. And as our instruments improve, the fog of uncertainty slowly lifts. Some theories will fade away, others will gain traction, and a few may eventually become accepted as part of our understanding of reality. The journey from bizarre hypothesis to accepted fact is long and uncertain, but it is fueled by the very tension between what we can measure and what we can imagine. That tension is where the next breakthrough will come from, and it is the reason we keep looking up, keep listening, and keep asking questions that seem to have no answers. Even incorrect theories push research into bold new directions. The search for dark matter, for instance, would not be as intense if modified gravity had not challenged the assumption that invisible particles explain galactic rotation curves. MOND forced astronomers to design experiments that could detect particles with extremely weak interactions, leading to underground detectors like those in deep mines and space-based observatories that look for faint signals of annihilation. Without that provocation, the hunt might have remained a quiet theoretical exercise. Instead, it became one of the most active frontiers of particle physics, with billions of dollars invested and thousands of scientists involved. Whether dark matter is ever found or not, the drive to test it has produced new detector technologies and a deeper understanding of how to probe the invisible universe. The holographic principle has played a similar role in motivating quantum gravity research. It suggested that the deepest description of gravity might not involve particles or fields at all, but something more fundamental like information stored on a surface. That idea pushed physicists to explore new mathematical frameworks, such as the AD/CFT correspondence, which connects a theory of gravity in a higher dimensional space to a quantum field theory on its boundary. This correspondence has become one of the most powerful tools in theoretical physics. used to study black holes, quark-gluon plasmas, and even certain condensed matter systems. The experiments that might test these ideas are still distant, but the mathematical insights they generate are already paying dividends in other fields. Bizarre theories also force scientists to re-examine assumptions they had stopped questioning. The fine-tuning puzzle, for instance, made cosmologists reconsider the very definition of a law of physics. If the constants could be different, then perhaps the laws are not universal but local, and the multiverse becomes a serious hypothesis. That line of thinking has inspired efforts to measure the equation of state of dark energy with ever greater precision, because if that number ever deviates from -1, it would open the door to a completely new understanding of cosmic acceleration. Without the bizarre idea that our universe might be fine-tuned by chance across a vast multiverse, the motivation to pin down that number might be far weaker. The constant pressure from these ideas has made astronomy and physics more creative. Researchers design experiments that would have seemed absurd a generation ago, like looking for quantum effects in biological systems or searching for tiny glitches in the cosmic microwave background that could betray a previous cosmic cycle. They build detectors that can sense a single photon or a single gravitational wave, pushing engineering to its limits. Every failed test of a bizarre theory narrows the possibilities and sharpens the questions that remain. The process is slow and humbling, but it is how science deepens. This relentless questioning leads eventually to philosophy, because when the evidence runs out, we are left with the meaning of what we have found. If the universe is a simulation, what does it mean to be a conscious observer inside it? If time is an illusion, what does it mean to have a past or a future? These questions are not just idle speculation. They shape how we view our own existence and our place in the cosmos. Bizarre theories do not always give us answers, but they force us to ask better questions. And that, perhaps, is their greatest gift. The search continues, and the next discovery may come from a hypothesis that today seems impossible or absurd. These ideas ask for a sacrifice of certainty. Throughout human history, every major shift in our understanding of the cosmos has demanded that we let go of something we once held as absolute truth. When Copernicus placed the Sun at the center of the solar system, it meant that Earth was no longer the privileged stage of creation. Humanity lost its physical centrality. When Darwin revealed that life evolved through natural selection, we lost our unique place in the biological world. And when Einstein showed that time and space are relative, we lost the comfort of a universal clock ticking the same for everyone. Each of these paradigm shifts was met with resistance, sometimes fierce, because they forced us to see ourselves not as the fixed center of reality, but as small participants in a vast, indifferent universe. The theories we have explored in this journey demand a similar kind of letting go. If the multiverse is real, then our universe is not special. It is just one bubble in an infinite foam, and the laws we have discovered so carefully are only local bylaws, not universal truth. That is a blow to the idea that we can ever know the ultimate laws of nature. If time is an illusion, then our sense of past, present, and future is a kind of waking dream. And the flow we feel so deeply is just how our brain interprets a frozen block of space-time. That challenges the very foundation of personal identity and memory. If consciousness is a fundamental part of the universe rather than a byproduct of brain activity, then our inner experience is not a private accident but a window into the deepest structure of reality. That elevates the observer to a role that is both exhilarating and unsettling. These shifts are not easy to accept. They ask us to trade a coherent picture for one that is stranger, less intuitive, and sometimes deeply humbling. Yet science has always required such trade-offs. Every time we have peered deeper into the fabric of reality, we have found that the world is not built the way our common sense expects. The atoms we are made of are mostly empty space. The stars we see are actually looking into the past. the very ground beneath our feet is hurtling through an expanding cosmos at unimaginable speeds. Our brains evolved on the African savanna to track prey and avoid predators, not to understand quantum mechanics or the curvature of space-time. So when a bizarre theory challenges our intuition, it may be a sign that we are finally brushing up against the genuine nature of things, rather than a sign that the theory is wrong. The most difficult conceptual shift of all may be the acceptance that some of these questions might never have definitive answers. The multiverse, the simulation hypothesis, the nature of time, these are ideas that push against the limits of what can be tested. They force us to sit with uncertainty, to hold two possibilities in our minds at once without demanding resolution. That is a deeply uncomfortable place for a species that craves explanations. But it is also a place of intellectual honesty and humility. We do not know if we live in one of infinite universes or in a simulation. We do not know if time is real or emergent. And that not knowing is not a failure. It is the engine that drives the next question, the next observation, the next leap of imagination. As we approach the end of this journey, we are left with a single, profound truth. The human desire to understand the cosmos is not diminished by the strangeness of the answers. If anything, it is amplified. Every bizarre theory we have explored is a testament to that desire. It is the same desire that drove ancient astronomers to map the stars, that led Newton to formulate gravity, that sent humans to the moon. It is the desire to find our place in the grand story of the universe, no matter how small or strange that place may turn out to be. The answers may be unsettling, but the search itself is what gives meaning to our existence. And that search continues not despite the uncertainty, but because of it. The cosmos remains open, and so do we. From particles that exist in two places at once to a universe that may be a hologram, from the echo of a previous cosmic cycle to the phantom force that could tear everything apart, each theory we have explored peels back a different layer of the ordinary. They all share a common thread. The universe we wake up to every morning is not the full story. The solid ground beneath your feet, the steady tick of the clock, the feeling that you are a unique individual making free choices, each of these certainties has been questioned by the ideas we have covered. And that is exactly what science is supposed to do. It is not a collection of settled facts. It is a process of constantly testing the edges, of pushing into the unknown, of asking what happens when we take the math seriously, even when it leads to places that feel like fiction. The 25 theories we have walked through are not just curiosities. They are a map of the frontiers where our current understanding meets its limits. Some of them will eventually be ruled out by better data. Others may become the foundation of a new worldview, but the important thing is that we keep asking, keep watching, keep wondering. If you have made it this far, you are part of that quest. The most bizarre theory of all may still be waiting, hidden in an observation we have not yet made, in a number that has not yet been measured, or in a question no one has thought to ask. Stay curious, keep your eyes on the sky, and if you want to go deeper into these mysteries, hit that like button, leave a comment with the theory that unsettled you the most, and subscribe so you do not miss the next journey into the strange and the real. After all, the universe is still writing its story, and we are just beginning to read it.